does. Spontaneity, I think. Spontaneity.
It's like March about 2015.
All right. I don't see. Anyway, I'll just talk about it instead. Right here. Let's talk about energy entropy. Have you ever heard of energy entropy? Energy entropy. We have something called chemical potential energy. Let me just review this. That from a while ago. I did this in Chem 1A, where we're looking at methane and O2. This is the energy here, going to CO2 plus H2O. I just chose the liquid. Methane and oxygen. If I have a mixture of methane and oxygen, would that be at a higher energy or lower energy than a mixture of CO2 and water? Higher energy. Higher energy, what does that mean? Does that mean it's at a higher temperature? Is the methane and oxygen at a higher temperature? No. Because this is going to be methane and oxygen, this is going to be at 298 Kelvin. Right? And so if I fill up this room with methane, there's oxygen in here, I have a mixture. And that mixture is going to be a high energy mixture, although it doesn't feel like a high energy mixture, right? But you know it's a high energy mixture because if I keep filling this room up with methane, you're going to get uncomfortable, probably. You're either going to worry about asphyxiation or worry about fire explosion, right? And then if there's a fire explosion, wow, that's a lot of heat generated. So when methane and oxygen combust, how hot is that flame? Very hot, 800 degrees C, let's say. And so this is going to be CO2 and water at 800 degrees C, or what's the temperature of the CO2 and water here? This is going to be at 298. Well, what happened to all that increase in temperature? Where did that go? Yeah, that increase in temperature was all released to the surroundings, the rest of the universe, we call that, as heat, right? If we do this under, if we do this under constant pressure, is work done? Under constant pressure, actually work is done. We're going from 75 liters to about 25 liters. So we'll just say delta H is just going to equal QP, right? The heat that's released. Remember that? Stop. All right, so this is at 298. This is at 298. So what's changing? Because if we're looking at the total energy is equal to, well, U initial is equal to what? Well,
Kinetic plus potential.
absolute. Kinetic plus potential, right? U final is equal to kinetic final. Oops, this is initial, this is initial. This is final plus potential final, right? Did the kinetic energy change between initial and final states? No. And so the kinetic energy is the same, so there's no change in kinetic energy. The change was all in potential energy. And so delta U is just equal to delta PE. Delta EK is 0. All right, so this tells us two different types of energies. What is heat? Heat. Heat is kinetic energy, right? Heat is transfer of kinetic energy from a hot body to a cold body. And so this energy is being released to the surroundings as heat. You know, it got very hot, you let it cool down, it's back down to 298, but the surroundings absorbed all that heat, which is just all these kinetic energies. And so do you see what we just did to the energy here? What did we do to the energy in this reaction? We converted potential energy into kinetic energy. Now, what do you think is more ordered? What do you think, the potential energy or the kinetic energy? Potential energy is more ordered, meaning it has a lower entropy or higher entropy? Lower entropy. And so we're going from lower entropy, potential energy, to higher energy, or entropy, higher entropy, kinetic energy. You know, you can't do as much with heat. For example, if you have electricity versus heat, you could do a lot more with electricity than with heat. And therefore, they call, what do they have? Energy values or something like that? For electricity versus heat. You know, electricity is more valuable, right? Because you can convert electricity into many different things. You can convert it into work, into heat. But what can you do with heat? Well, you could convert it into work, but it's not very efficient. Converting heat into work. You know, you can make a steam engine. Steam engines are very inefficient. But if you have potential energy, you know, in theory, you could convert all this into work. If there was no heat loss, it would be 100% converted into work. Does that make sense? All right, so this brings us to how we're going to figure out delta S of the surroundings. Do you know how we're going to figure out delta S of the surroundings? Because delta S is related to, and so let's talk about this. We know that delta S is equal to Q reversible over T. And so there's some kind of heat transfer at a given temperature. And so delta S of the surroundings is equal to Q of the, I'll just say Q reversible of the surrounding. Doing this reversibly, there's some restrictions there, but I'm not going to talk about it. It's just a reversible process. Heat can go in, heat can come out, that kind of thing. Over T. But we know that from the first law of thermodynamics, what do we know from the first law? Yeah, energy is conserved. And so if the surroundings gains or loses that heat, then where did that go? Or where did it come from? And so Q of the surroundings is equal to minus Q of the system. And then you guys know how enthalpy is defined. How do you define enthalpy? I ask that because I think nobody can define it usually. Every time I ask, what is the definition of enthalpy? No, actually, maybe a couple of people can define it. What is the definition of enthalpy? There are lots of ways to define it. Just give me one. Yeah, heat restricted to make it a state function. That's a good definition. And so heat is normally a path-dependent function, but you can force it in to become a state function by restricting it to constant pressure. And so here, the first thing we're going to do is we're going to restrict this to constant pressure. And so what we got here is we got Q sub P, a reversible system, over T. So we restricted to constant pressure. Is there any other restriction? Yes, there is. What is the other restriction? It has to do with, not moles, it has to do with work. Good. Wow. You have a good memory. Usually when I ask this question, nobody answers, so that's good, Arthur. We restrict the work to what kind of work?
P delta.
Yeah. And so it's minus P delta V because this is work of the system. Work of the surroundings would be P delta V. Work of the system is minus P delta V, which is going to change this. So now we can define Q as delta H. And so this is going to be delta H of the system over T. So now what we have is we have delta S of the universe. Delta S of the universe is equal to delta S of our system plus delta S of our surroundings. You know, whatever the total change of the system's entropy combined with the total change of the surroundings entropy. Now the surroundings entropy is just going to be delta S of the system, you know, minus delta H of the system over T. And so that means that, well, let's multiply T by both sides. So we get T delta S. T is a state function as well. T delta S of the universe is equal to T delta S of the system plus, minus delta H of the system over T. Oops, not over T. We'll just leave it like that. Okay, then we're going to multiply by, actually, are we going to multiply? Yeah, let's multiply by negative. So we get minus T delta S of the universe is equal to delta H of the system minus T delta S of the system. But when we multiply by negative, that changes because we know the universe has to be greater than 0 for this to be spontaneous. And so if we multiply by T, that's still, it has to be greater than 0 to be spontaneous. But now when we multiply by negative, we want this to be less than 0. We just flipped it, the sign. So T is a state function. T is a state function because temperature just, delta T just depends on the final temperature and the initial temperature. It doesn't depend on the path, right? So T is a state function. Delta S of the universe is a state function. And so this is a state function. And so that state function minus T delta S of the universe is going to be our definition of delta G. We could call delta G of the system. This is called the Gibbs free energy. That's a new state function. Named after Gibbs, the physicist, thermodynamics. And so just to simplify this, delta G of our system is equal to delta H of our system minus T delta S of our system. So this is the second law of thermodynamics, rewritten. And this has restrictions, of course. What are the restrictions here? Constant pressure and P delta V work right now for our delta H. Now, we want this to be less than 0 for driving force. You know, driving force is going to make this spontaneous. And so this is a much easier read of the second law of thermo, because the second law of thermo, I mean, to figure out the entropy of the universe is very difficult, but we know about energy. And so if delta H is positive, what does that mean? Delta H is positive means that we're dumping heat from the system into the surroundings, but it's not just heat, because if it were going from heat to heat, right, it seemed like the entropy would be break even. But if delta H is endothermic, that means we're going from chemical potential energy into heat, which means that the entropy's got to be going up. And so when we see delta H endothermic, that means the entropy is increasing for the surroundings, for sure. Does that make sense? No? And so in other words, this is our energy term. You know, we want to minimize energy, right? Because we already said this. With delta H less than 0, that's good. Energy is going down. We want energy to go down. But if delta H is less than 0, that means that the energy entropy of the universe has just gone up. And so that means the delta S for the energy has increased, has gone up, is greater than 0. And so this is, yes, the second law is just the entropy of the universe increases, but we can get a read of the entropy of the surroundings based on what's happening with the system. Here. And so here, if delta H is greater than 0, then that means the opposite. If delta H is greater than 0, that means it's endothermic. It's got to take in energy from the surroundings. And the opposite would happen. This would go down. Okay, so there are two ways that are commonly stated for the second law of the two equations. One, delta S of the universe is greater than 0. Number two, delta G of the system is less than 0 for spontaneous processes. So now it's easy to compare. Now we can compare these two. Compare entropy and energy. We know how to calculate both of those, right? Delta H, appendix D, delta S, appendix D. It's a pretty straightforward calculation. And we'll see. And so we'll take a look at some values here and interpretations of that. And so when we look at delta H, we have two choices, delta S and delta G. If delta H is negative, that's favorable, right? If delta S is positive, that's favorable. And so we have two driving forces working in unison, which means this is going to be negative and spontaneous. But, you know, temperature can influence things, so we're going to say spontaneous at all temperatures. If delta H is positive, that's unfavorable, and if delta S is negative, that's unfavorable. And so this is going to be positive, and so it's going to be non-spontaneous at all temperatures. But what can happen here is there can be a conflict. For example, delta H is favorable, but delta S is unfavorable. And so if the energy term is favorable, but the entropy term is unfavorable, then you want to minimize the entropy term. One way we can minimize the entropy term is by decreasing the temperature. And so what we can say is this is going to be spontaneous at low temp, non-spontaneous at high temp. Low and high is relative, depending on what we're looking at. Okay, or the energy can be unfavorable, but the entropy can be favorable. And so if the energy is unfavorable, but the entropy is favorable, then we want to favor the entropy to force the reaction to go by increasing the temperature. And so this would be spontaneous at high temp, non-spontaneous at low temp. We can determine these easily at 298, and so we can determine the spontaneity various reactions at 298 because we have the data at 298. And it's fairly straightforward. And so what we'll see here is this. Fine. Are we out? No, we still got time. Okay. Continue here. Well, let's put some numbers on here. There's a table in here. I don't remember exactly where it is. But the table looks like this. If we look at some delta G values and then compare it to like K, or just let's just look at delta G values right here. You know, 50, 100, 200. You know, minus 50, minus 100, minus 200. And so if we have delta G values between 50 and minus 50, then you know what we see is not one side is particularly favored over the other side. And so we typically experience an equilibrium between reactants and products. As we start going up higher and higher, what we're going to see is this becomes increasingly non-spontaneous. So typically we have, you know, no reactions up here. No reactions would be like, you know, a delta G greater than, let's say greater than 100 would be equivalent to like a K being like 10 to the minus 10, you know, 10 to the minus 15, 10 to the minus 20. And down here, we're looking at very spontaneous reactions here. And so these are the typical values we're looking at, you know, 100, 50, hundreds of kilojoules for that delta G. All right. So let's go back to this reaction here that we were looking at earlier. What number was that? 77. Okay, 77. Okay, nitrogen plus oxygen yields 2 NO. Delta H was positive. Delta S was positive. And so positive and positive says that this reaction should be spontaneous at high temperature, non-spontaneous at low. And so if we keep increasing the temperature on this, we should be able to make this reaction happen. And so let's take a look at this reaction again and then do some calculations here, because earlier we were asking what the criteria was. For this. And so going back to this problem, and we still aren't finishing this because you still need one more thing in order to complete it. But let's go ahead and calculate our delta G. This is going to be a standard condition at 290 Kelvin. And so what do we do here? Well, we need our delta H naught, 290 Kelvin, minus T delta S naught at 298 Kelvin. The temperature is going to be 298 Kelvin. And so what was delta H naught again? 180.5 kilojoules. T is 298 Kelvin. Delta S naught was 24.9 joules per Kelvin. Well, the units aren't going to work out. You know, I got kilojoules here, I got joules here. The Kelvin nicely cancels. Yeah, so we need to divide this by 1,000. So 1 kilojoule is equivalent to 1,000 joules. And so now the joules cancel. Now we got kilojoules. And so let's see what this is here. Plus 173 kilojoules. When you see a number that big, you're thinking highly non-spontaneous. This reaction just has no driving force. Right? It shouldn't happen. But while we do see that, you know, the entropy is kind of favorable. So what favors higher entropy? Well, higher temperatures, right? See that. So, non-spontaneous. I'd say highly non-spontaneous, which is good because NO is toxic. We don't want to be breathing a lot of NO in this room as we're just sitting here. It's colorless gas. It's rapidly oxidized to NO2, which is a brown gas. But, this is a highly non-spontaneous. So the question is this. What are the current constraints of this? One, it's 298 Kelvin. And two, what's the other constraint? The pressure. What is the pressure? Well, appendix D is 1 bar. And so, you know, we know that this has to be for 1 bar under standard conditions. And so what we're going to do here is this, we're going to ask this question, at what temperature will this go spontaneous? That's difficult because in order to calculate at what temperature this goes spontaneous, we need to have the delta H value at that temperature, but we don't even know what the temperature is, do we? And so it seems like it's an impossible problem to solve because the same thing with the delta S, we don't know what the temperature is. We might be able to look it up in a table, you know, the delta H and the delta S, not in our book, but in other books. So somebody's probably determined delta H's and delta S's at higher temperature, right? And so this is going to be important here as far as temperature dependence. Delta H and delta S don't change much with T. So for example, if you vaporized a mole of water at 298, so you went from H2O at 298 to H2O gas, H2O liquid at 298 versus H2O gas at 298. So we vaporize that. There's going to be some delta H associated with that and a delta S associated with the vaporization process. Right? And so here we vaporize that. But let's say I increase the temperature to 300. So this is H2O liquid at 300 is going to have higher entropy, but so is H2O gas. And so both of these are going to be at 300. And that means the delta H isn't going to be that different, nor is the delta S. Does that make sense? And so it's going to be at T, at a certain T, at a certain T. Delta G is highly dependent on temperature. this was not the easiest way to calculate delta G. There. There's an even easier way to calculate delta G, which I'll talk about in just a minute. But what we can do is this. If we want to figure out the temperature at which this becomes spontaneous, then what we want to do is we want to go from a delta G that's highly positive. You know, the delta G is highly positive, and then we want to drop it down to a delta G of 0. And then if we go negative, then it's going to be spontaneous, right? And so when delta G goes to 0, that's when it should become spontaneous. So delta G equals 0. Well, how can it equal 0? Well, we need a certain temperature to overcome this. And so this delta H is positive. It's endothermic, right? And so we need some temperature to make the entropy bigger so it cancels out the delta H. What is that temperature? Well, the temperature is going to equal delta H over delta S. But the problem is the delta H has to be at that temperature and the delta S has to be at that temperature. But what we're going to say is that, well, if delta H and delta S don't change much, then we're going to just say that we're going to apply the 298 value here and the delta S at 298 here to come up. It's not perfect, but it's going to be close. Otherwise, it is an impossible problem to solve with what we have right now. And so if we make this approximation, then we should be able to solve it. And so what is delta H? Was it 180.5 kilojoules? And delta S? 0.0249 kilojoules per Kelvin. Kilojoules canceled out, that leaves us with Kelvin. What temperature should this go spontaneous? 7,249 Kelvin. Wow. 7,249 Kelvin. How hot is that? Yeah, this is about 1,000 Kelvin, this methane. Now, if you burn a hydrogen flame, it's hotter. I don't know if we can achieve that. That might be a hard temperature to achieve, unless you had something like a fusion reactor or something like that. This is a very high temperature. So very high temperature is required to make this spontaneous. But you know what? We could play with the temperature, but we could also play with the pressure, because right now we're constrained to a pressure of 1 bar, but if we did change the pressure, maybe that might help as well. And so what we're going to do is, doing these delta G calculations is really easy, you know, with appendix D. And in fact, it's even easier than this. You know, there's an easier way to do delta G. Let's talk about it. You know, delta G of reaction is equal to the sum of nu P times the delta G of formation of the product minus the sum of nu R delta G of formation of the reactant. This looks like the Hess's law type deal. Where do I get the delta G's of formation? In appendix D. That's what the middle column was in appendix D, delta G's of formation. And so this is an even easier way, but you know, again, I'm restricted to 298 Kelvin with appendix D. So this is a bit more restricted because this doesn't show any influence of temperature. We're stuck at 298. With the other delta G equation, at least we can play with the temperature and assume that the delta H's and delta S's aren't changing much. And so we can calculate delta G. We can determine if it's spontaneous or non-spontaneous. But what we want to do is we want to start manipulating the reactions. And the way we can manipulate the reactions is by changing the temperature or manipulate the driving force. is by changing the temperature, changing the pressure, or changing the concentrations. Temperature, pressure, concentration. And so for changing the temperature, this is how we do it. We just use the delta G is equal to delta H minus T delta S, and we make an assumption. Okay, at what approximate temperature will an equal molar mixture of N2 and O2 be 1.0% converted to NO gas? All right, and so this is going to require some more relationships here. And so delta G, the driving force, must be related to K in some way, you know, the equilibrium constant. Because if you have a large driving force, then K must be very big to favor the products. If there's no driving force at all, then K must be very small because it favors no reaction. And so what is the relationship between delta G and K? So, because this is the next thing we want to do is figure out delta G and K.
Professor's 10.
Oh, okay, let's stop here.